Yo, imagine if group elements were like basis vectors for a linear space, and you just like took linear combinations of them with coefficients from like the complex numbers or like some other field, and you could have like a vector space, but like it's made out of group stuff. Whoa. That's kind of what a group algebra is. Let G be a finite group with elements G1 through Gn, where n is the order of the group. And then let our field be the real numbers or the complex numbers, because we're not masochists. Then we say that V is called Fg, right? Our field and our group. We call it V because it's going to be a vector space. And we say that V is the collection of elements of this form. That's just a linear combination of group elements. I came from physics, so I like to use the summation convention. Usually there's an upper index and a lower index, but I'm just gonna do it like this because I'm kinda lazy. Now, if we take two guys, S and T from Fg, that means that S and T have this form. They're a linear combination of group elements scaled by some element of our field. All the lambda i's and all the mu i's live in our field. Then we can upgrade V to a vector space by defining addition to look like this. S plus T, well these are sums, remember? So we just factor out the group elements over here and we sum the scalars. I also forgot when I was writing this that we need to worry about scalars as well. For it to be a vector space, we need that scalar multiplication, right? So if alpha lives in our field, alpha times S, which lives in Fg, right? It's a linear combination of group elements. We just multiply the whole thing by alpha, right? It's just a scaling. You can pull it inside your sum. Sorry, I almost forgot about the scalars. That's important. Now, as I was saying, a group algebra is just linear combinations of group elements over a field, F, with addition as you'd expect, upgrading it to a vector space. It also needs a distributive multiplication to be an algebra, like we talked about in the last video. But there's a natural way to define this. It's actually really straightforward. If we take our two S and T's from our Fg, like we had before, right? This is our group algebra. We can define our product just as you'd expect, right? This is a sum, you just multiply everything out. Bam. Forget about that. I screwed that up. If we look at an example, this all becomes really, really obvious. So I've written one up for you guys. Let's pick our field to be the real numbers. Why not? Let our group be the cyclic group of order 3. Now consider the group algebra, V with a multiplication, where V is equal to RC3, right? That's our group algebra. And our multiplication is how we just defined that. If we let A generate A3, so then all elements of V are of this form, where S0, S1, and S2 are all real numbers, right? Here are our group elements. We have one scaling factor for each of our group elements. I picked C3 because there's only 3 of them, and then my life was a little easier. You could see what elements would look like for any discrete group that you like. Now consider these two specific examples. We have 2e plus a. There's still a scaling factor for a squared, but it's 0. So we would usually just write this out as 2e plus a. And our second element is e plus a half a plus 3a squared. So this one has a scaling factor that's non-zero for all 3 of the group elements. So these guys are vectors in our vector space, which means we can add them. So if you add them together, it's exactly as you would expect with our group elements as the basis elements for our vector space. So when we collect like terms, just like in high school, we can then factor out 3 because of our property with the scalars. Remember I had that foldy paper? That's why we can factor here. We can also subtract, adding inverses, negative add. S minus t, well, this is just minus 1 times e, is how we can think of this. In fact, I'm gonna write that down right now. See, this is just addition, and we can define our additive inverse as multiplying by negative e. Right? This is negative 1 times e, that is definitely an element in our vector space. And the subtraction goes exactly as you would expect. Then we can multiply, again, just like we're in high school with polynomials. Just remember that this example looks especially like polynomials because all group elements are just a power of the generator. But in general, groups are not just generated by one element, just the cyclic groups. So that is purely a coincidence for this example that it looks especially like we did in high school, but it's always easy. You just expand and simplify, right? You collect your like terms. So this got a little messy over here, but you just multiply everybody by everybody. Distribution, nothing fancy. And then I simplified over here. But in the end, you get an element of V, just coefficients times your group elements, which is the basis vectors. All right, guys, so hopefully group algebras make a little bit more sense now. They're kind of weird and interesting, and they're super important for something called the regular FG module of a group, or a regular representation of a group, which is really straightforward if you understand how group algebras work. You get this awesome representation for your groups that's always faithful. And that's what we're going to be talking about in the next video. Thanks for watching. Have fun doing math. If I can figure this shit out, so can you. Have a great day. Bye.